The following is a special lecture titled Death by Black Hole. The lecturer is Professor Neil Tyson. Professor Tyson is the Frederick P. Rose Director of the Hayden Planetarium and a visiting research scientist and lecturer in the Department of Astrophysical Sciences at Princeton University. He is also an astrophysicist at the American Museum of Natural History. Professor Tyson received his B.A. in physics from Harvard University, his M.A. in astronomy from the University of Texas at Austin, and his Ph.D. in astrophysics from Columbia University. A prolific writer and columnist for Natural History magazine, he is the author of 6 books, including One Universe, At Home in the Cosmos, and The Sky is Not the Limit, Adventures of an Urban Astrophysicist. Professor Tyson can be seen frequently on national news programs reporting on topics of cosmic discovery.
Today's lecture is called Death by Black Hole. And the point of this session is to sensitize you to what kinds of havoc a black hole can bring upon its environment. The 2 principal kinds of black holes. One, the most familiar kind, most familiar to an astrophysicist, is when you have a star much more massive than the sun. It runs through its evolutionary cycle. And in the end of its life, it runs out of fuel in its core, and it can no longer support itself from collapse. Gravity takes over, gravity wins, and it collapses the system all the way down, taking all of that mass and compressing it into a tiny little volume. The force of gravity that you experience if you're standing on an object is not only related to how much mass is there, but also how close you are to the center of that object. The closer you are, the more you will weigh. The more mass is in the object, the more you will weigh. All these factors contribute to our analysis of what a black hole will do to its environment, as is the subject of today. If we look at our first slide, we're going to use a person as an example. But in fact, what we describe happen to a person is precisely what will happen to a star if a star, minding its own business, journeyed too close to a black hole. And we can go beyond stars in this discussion and think about star clusters. Clusters of stars having thousands or hundreds of thousands of stars within them. If they wandered too close to a black hole, we'll learn what effect the black hole has on the structure of that star cluster. We can ask ourselves first, what is a black hole? Let's just get that out of the way. What is a black hole? Here I am standing on Earth, and I have no problems jumping, but every time I jump, I come back to Earth. Some people jump and stay up longer than other people. It's because they jumped higher, not because there's some magic in their basketball shoes. So the fact is, if you toss something with higher speed, it will go to a higher elevation before it comes back. That makes sense, of course. If I do that experiment with my shoe, I only throw it a little bit, it goes up and down. Throw it harder, it takes longer to come back. Ask the question, is there a speed with which I can toss my shoe so that it never comes back, thereby violating everything your grandparents told you, that what goes up must come down? Well, in fact, there is a speed with which I can throw my shoe from the surface of the Earth so that it will never come back. And that speed, it has a name, it's called the escape velocity, quite sensibly. And for Earth, that speed is much faster than I can throw. It's 7 miles per second. That's very, very fast, but it's not magically fast. The Apollo astronauts, back in the 1960s and 70s, en route to the moon, they first went into orbit around Earth and then fired the 3rd stage of their rockets to leave Earth and go to the moon. Their speed at that moment was very nearly equal to 7 miles per second, so that they could escape the gravitational tug of the Earth, preventing them from coming back, and they go all the way to the moon with that speed. This escape velocity concept, it's quite intuitive, and it also allows you to understand why on the moon, that has a lower surface gravity, it also has a slower escape velocity, only about 1.5 miles per second. The sun, of course, you can imagine, has a much higher escape velocity, nearly 400 miles per second. So in other words, if we're just sitting there on the surface of the sun, flame-proof suit, and you wanted to toss something, almost everything you ever did, it would all come back to the sun and burn up. If you hit 500 miles per second, it'll leave the solar system from the surface of the sun. So this notion of escape velocity is quite useful when you're thinking about launching something from the surface of an object. Well, let's put a pin in that and ask, is there an object whose escape velocity is so high that you could never escape? Well, what's the fastest possible speed? We know what that is. It's the speed of light. 186,000 miles per second. At that speed, it has no problems leaving Earth. I take a flashlight, the light goes straight up from the surface of the Earth. It doesn't come back. It doesn't struggle to leave the gravitational tug of the Earth. It's gone. No problem, because 186,000 miles per second is much, much bigger than 7 miles per second. Not a problem. But imagine if the gravity of Earth were greater. If we had much more mass, or we were in a much tinier volume, or both, then the escape velocity gets higher and higher and higher and higher. Let's look at this illustration. This just compares the moon, the Earth, and the sun. Moon has a smaller escape velocity than Earth. In turn, a smaller escape velocity than the sun. Imagine another object whose escape velocity were so high that it was the speed of light itself. What would then happen to your beam of light? That beam of light, if I turned it on, by the way, if the escape velocity were just the speed of light, the light would just barely escape the gravitational tug of that object. If it was more than the speed of light, guess what would happen? I'd turn on the light would go up and come right back down to the surface of the planet. Just the way my shoe did when I tossed it on the surface of the Earth. There are equations that describe this. What does the escape velocity depend on? I've drawn two terms here. This one on the left is just the sort of the energy with which you toss the object. And that energy comes from, it's the kinetic energy of motion. That's what this V is doing here in the equation. M is just the mass. On the other side of the equation is a measure of how much energy gravity is taking away from you if you are launched from the surface of the object. And if you set those to be equal, you can get a sense of how much velocity it takes to reach infinity. That's exactly what's here in the box, the escape velocity. And notice, the mass of the object is in the numerator. The more massive is the object, the higher is your escape velocity. And the radius of the object is in the denominator. The smaller the object, the higher your escape velocity. No better introduction exists to black holes than that equation, because black holes have a lot of mass in a small volume. They're getting 2 for 1 here. A high numerator and a small denominator. They've got an escape velocity that is, in fact, the speed of light or greater. Now, that's a hand-waving, brief introduction to black holes, but now let's see what effect they have on their environment. Sure, they're going to sort of suck things up out of the environment around them using their powerful gravity. That's obvious. But there's something a little more sinister that goes on in the vicinity of a black hole that requires us to think a little differently about its gravity in its vicinity. What we need to do is ask the question, now that the black hole prevents you from escaping it, because you're not going to travel at the speed of light, because it has such high gravity, what is the change of gravity between near the surface of the black hole and regions above it? It's not all the same. As you get closer, the gravity feels stronger and stronger. Now, we have a word for this. If part of you feels a stronger gravity because it's closer to the object than another part of you, there's an effect that tries to stretch you out a little bit. Those are called tidal forces. The root word of that comes tides. A very familiar word on Earth with regard to Earth's oceans. Earth's oceans feel the tides from the moon. We know this. You look up moon tables in your if you have a home on the shore, you want to know when the tide comes in and out, you look up the moon tables, and they will tell you this. Well, what is a tidal force anyway? I'm standing here on Earth. My feet are closer to the center of the Earth than my head is. The closer you get to the center of the object, the higher is the gravity. So my feet feel a stronger force of gravity to the Earth than my head does. And I can calculate that. You know, it's not that much of a difference. It's just not. Because Earth is enormous, 8,000 miles in diameter, and I'm just 6 feet tall standing on top of it. So here I am, 4,000 miles to the center, and then 4,000 miles plus 6 feet. That difference, you put it in the equation, you don't even notice the difference. So I'm not walking around saying, I feel lightheaded because there's not enough gravity on my head compared to my feet. It's not a problem. We're all just happy walking around on the surface of the Earth. Not a problem. But the entire Earth feels this tidal force because Earth is large compared to the distance to the moon. So here's Earth, moon is out here, the gravity of the moon, this side of me is 8,000 miles closer to the moon than this side of me is. So I'm Earth, I'm going to feel that. Now it's 8,000 miles on a 250,000 miles, it's still small, but it's enough to notice. And that difference creates a bulge, not only in the solid Earth, but also in Earth's oceans. And that's where you get the familiar diagram of Earth. Here's a schematic of Earth surrounded by an ocean. Imagine there was no moon, and there's the ocean just perfectly the same depth all around. Bring a moon into the picture, you get a distortion. And that distortion is the effect of this side of the Earth feeling a strong gravity, the middle of the Earth feeling a slightly less gravity, and the back side of the Earth even less gravity. Anytime you have a difference in force across an object, it stretches. That's all there is to it. It's not deeper than that. Tidal forces, they can be bad for an object because here's something just happy being solid. It feels this external force trying to stretch it, and if you're made of rubber, fine. But if you're made of something solid, that could be bad. That could be bad. For example, what would happen if your head were the size of Earth? Well, but before we answer that question, let's ask, I'm often asked, people say, well, Professor Tyson, if the moon affects the oceans on Earth in just this way, the oceans are made of water, and the human body is mostly water, we learned from our biology class, then what effect does the full moon have on human beings? Does it really make you a lunatic? And, well, you know, I don't know the answer to that question. But let me instead answer a different question. I can calculate the tidal force across your skull from the moon. You line up your head and the moon is in the window, so the moon is pulling on this side of your head more than it's pulling on the... I calculate how much that is. I write down that number. Very small number, as you would expect. Now, I don't know the biology of that force on your head. I don't know. But there's something else I know. The force on your head of a down pillow that happens to sort of lean against it in the middle of the night is 1 trillion times greater than the tidal force on your skull from the moon. Yet I don't see books written about the effects of pillows on your behavior at night, whereas they ought to, because that force swamps anything that would happen in the tidal force of the moon. Now, what is the problem? The problem is your head is not large compared to the distance to the moon. if your head were large, if your head were 8,000 miles in diameter, you'd have misshapen head, just like the shape of the earth, with untold consequences on your mental faculties. But that's not the size of our heads. So I don't need to lose sleep over this problem. But it is an effect of tidal forces that are directly, that can be directly calculated from standard equations of gravity. Now, let's ask a question now. Now that we understand how a tidal force will stretch you, it turns out because black holes are small, you can get pretty close to their center. And the closer you get to the center of an object, the stronger is its gravity. And the bigger becomes the difference between the gravity at the bottom compared to the gravity at the top. So let's imagine we were made of rubber, just to not get gory just yet. In this next figure, I've got a little man here, and I'm dropping him free fall to a black hole. Now, by the way, if you're in free fall, you are accelerating by the action of a force, in this case, gravity. If you're free fall, you're weightless. I don't recommend you do this experiment, but you can just trust me that if you were in an elevator and someone cut the elevator cord, the elevator falls, you fall, everything in your pocket falls, everything falls at exactly the same speed. If I'm holding a piece of chalk, if I'm holding my shoe, and I'm in the elevator, someone cuts the cord, if I let go of the shoe, I'm falling, the elevator's falling, the shoe falls. The shoe will just stay there in front of me. And I say, hey, the shoe is just floating. Someone outside looking says, you all are falling very quickly together. But to me, it looks like it's just a float in front of my eyes, because in fact it is. Now, if you're falling towards a black hole, you don't notice how strong the gravity is, any more than if you're in a falling elevator that you know how much Earth is pulling on you. You just don't know that until you start getting closer and closer to the black hole. All of a sudden, these tidal forces become real. They become significant because your height is now a greater and greater percent of your distance to the center of the black hole in the first place. So in other words, when you're far away from a black hole, you're only this tall, and the distance is this far. There's not much tidal force across that object. As you get closer and closer and closer, your height becomes more and more significant in this equation. As I drop you towards it, you say, oh, this is fun. This is wait a minute. I feel something happening. My feet are trying to pull away from the rest of my body. This will begin to feel uncomfortable. Now, this effect is initially, you'll just feel like you woke up in the morning and just stretched. If you stretch, you can usually grow a fraction of an inch. I put you on a rack, those old-fashioned medieval, that stretch out a couple inches. The human body is quite flexible in that regard. The vertebrae, and I'm told that old people shrink a couple of inches, with just these elastic things, but within reason, within limits. I drop you towards a black hole, there's a point where the gravity of the black hole is going to win. It's going to win in such a way that all the forces that hold your body together are not enough to prevent gravity from running its course. Now, what are those forces? We're made up of atoms and molecules. A chemist would say that we are held together by the forces, the chemical forces from one molecule to the next. Electrons sharing orbitals, that sort of thing. Well, to a physicist, since we're talking about electrons and protons, the actual force is an electromagnetic force. The force of attraction between electrons and protons. That's a powerful force. We don't think about how powerful it is because, in fact, we live with it. You can buy a child magnet for $3 at the checkout line of a store and wave it over a paper clip on the table. The paper clip will jump up and meet the magnet. The paper clip was there, held to the table by the gravity of the earth. But your little magnet stole it from the earth. Earth didn't stand a chance. All of its mass, all of its might, didn't stand a chance against a child's magnet. Electromagnetic forces are far greater than the ordinary gravity we experience. They're far greater than any. Another example, take the space shuttle. You've seen these powerful solid rocket boosters enable the thing to go into orbit. I've done this calculation. Go to the nose cone of the space shuttle and extract from it every electron that resides in the top 1 cubic centimeter. Take them all out. Take them and put them at the base of the launch pad. Now what you've done is you have separated two things that like hanging out together. Plus charges and minus charges. Opposites attract in the world of particle physics. So they want to be together. You just separated them, put them there. Now they still feel each other. They say, hey, we still want to get, you know how badly they want us to get together? Ignite the engines of the space shuttle will not be able to take off. Because the force between the electrons in the bottom and the leftover protons at the top exceeds the total thrust of that spacecraft. That's how powerful it is. We don't notice it because most matter is neutral. But if I were walking around positively charged and you were negatively charged, we'd have to use crowbars to pry us apart. So, when does gravity win out over these forces? Not on Earth, not on the sun, not in most places in the universe, except one, except black holes. If we were made of rubber, we would just stretch. I have some latent memory of there being a superhero, Rubber Man. I'd love Rubber Man to meet a black hole. That would just be fun. Or some other rubber character like Gumby. That would just be, just to watch Gumby do this, that would be fun. But here we go. If we were made of rubber, you just stretch. You would stretch as you fell toward the black hole. We're not made of rubber. We're made of tissue, muscle, held together by these electromagnetic forces. As you descend, your body begins to feel an ever-increasing tidal force of gravity from that black hole. Not only that, the black hole is more than just a place where light doesn't escape because it's not traveling fast enough. It's more than that. According to Einstein's general theory of relativity, the black hole's gravity has warped the fabric of space and time in its vicinity. Warped it. That's why when you turn on a flashlight on a black hole, it goes up and comes down just the way my shoe did, because in the case of a black hole, space does this. Space does that. If I stood here at that flashlight and looked up, I'd see the object that was here because space curved that way. Light goes that way. It bent the fabric of space. And in the bending of the fabric of space, it also funnels space down to the point of infinite density at the center of the black hole. So as you fall towards the black hole, no matter how broad are your shoulders when you started, the fact is you're going to have to end up funneling down to a single point. So two things are going to happen to you. You're going to be squeezed as you occupy the narrowing, continually narrowing volume of space as you approach the black hole. So you'll be extruded through space this way and stretched through space that way. One, because of the fabric of space-time, and two, because of the tidal forces of gravity. When I think of this, all I can think of is it's like toothpaste coming out of a toothpaste tube. This would be a bad day in the galaxy for you as you started descending towards a black hole. Because, in fact, we're not made of rubber. And what would actually happen is there's a point where these forces become so great that you snap into two pieces. You just snap. You'll snap right about in the middle. Right about in the middle. Just like that. While you're being funneled down. Then, those two pieces, previously one piece, now two pieces, those two pieces then snap into two pieces. And then they snap into two pieces. And this continues. You bifurcate all the way down until you become so close to the singularity of the black hole, descending rapidly through the event horizon. You'll just pass right through that. Be a little bit interesting because once you cross that border, you're not coming back out. So just say goodbye. You're descending down, bifurcating. You can only do this but so many times before you end up a long stream of atoms. Because the tidal forces become so great, it rips apart the molecules themselves. Now imagine that. How big is a molecule? It's just this big. It's thousandth the size of what I'm indicating here. And the tidal force across that becomes so great, the molecule can't stay together. That's how bad it gets as you approach the singularity. So no matter what you once were, you slide down to that singular point as a stream of atoms, funneled through space-time like toothpaste through a tube. Gravity wins. I don't know how else to say it. And while gravity wins, yes, it'll eat you, rip you into pieces. Gravity does that to stars that go too close. The gravity of a black hole. Star wanders too close. Stars are made of gas. The shape of the star begins to distort, and pieces of gas get flayed off the surface and spiral down toilet bowl style to the center of the black hole. If you're a star cluster minding your own business in mutual orbit, and you come near a black hole, the nearby stars get tugged, the far ones aren't tugged as much, and the star cluster gets stretched to the point where you start flinging stars out. In fact, most isolated stars in the galaxy, we believe, owe their origin to having been flung apart from a star cluster in which they were born, just because they wandered too close to something that had very strong tidal forces. We have here the anatomy of a black hole. You look down in the center, there's this little singularity. Singularity is a code word for we have no idea what's going on there. And Einstein's general theory of relativity doesn't help us. It stops at the singularity. We're dividing by zeros. And remember, since third grade, you're not supposed to do that. Einstein's theory of relativity gives us black holes. It gives us the Big Bang, the expanding universe. It gives us all of this. It does not tell us what goes on inside a singularity. We need other laws of physics. We got top people working on this. We've got string theorists. String theory is a hopeful path towards understanding what happens at the singularity. And we notice from this illustration that there's this sort of ghost-like sphere surrounding the singularity. Once you cross that border, that's it. You're gone from the rest of the universe because you will never travel faster than the speed of light. Kiss the universe goodbye. By the way, that's why we call them black holes. Light doesn't come out, nothing comes out, and we just call it as we see them in the universe. It's the way we do things. Just outside of the event horizon, that boundary between what's inside the universe and what's outside, you can escape. In principle, you just need a rocket that'll get you there fast enough. We can't go out and photograph a black hole because they don't give us any light. But you can photograph the smoking gun. You can photograph the smoke from the gun that had been fired. And at the moment, but we get a much better illustration of this from an artist's rendition. In this illustration, we have this spiraling disk. That was a gas cloud that wandered too close to the black hole. Or it wouldn't have to have been a gas. It could have been a nearby star that had, in its evolutionary stages, had swelled to become large and red. We call them red giants. And when you get that large, you can lose your material to nearby orbiting dense objects, such as black holes. And in this case, we have this spiraling disk of material descending down into the hole. So the black hole itself would obviously be right at the center of that. And all this material is trying to get in so quickly that it can't all happen at once. It gets hot, it gets highly radiative, and the energy is trying to escape, and it can't because the disk is in the way, so there's only one way it can punch out, and it's above and below, and you get jets. Right now we have the Hubble Space Telescope looking around the galaxy, as well as other telescopes. There's the Chandra X-ray telescope. We predict that X-rays are a signature of this jet phenomenon. We look around the galaxies for X-rays, coming from places that are not supposed to be giving us X-rays ordinarily. We see X-rays, then take an image of it. What do we find? We find disks of material. We find jets, just as we predict for what kind of havoc is being wrought upon the structure of our galaxy by these black holes. Now, there's one other kind of black hole, which is the subject of another lecture, but I'll touch on it now. It's the supermassive black hole. These black holes I've just been describing, they're all over the galaxy. They're rare, but we got tons of them. Supermassive black holes, as far as we can judge, there's only one per galaxy. And it's in the center, the galactic center. The mass of that black hole is upwards of 100 million times the mass of our sun. These are mondo black holes. These black holes, now, consider this, that they are so large that the tidal forces out beyond its event horizon are in fact not that great. It's got a lot of gravity, but remember, tidal forces are what rip you apart. And these black holes are so large, I could stand out there outside the event horizon, I'll be fine. I don't want to cross the event horizon, that's bad, but if I want to just sort of, if I want to be a daredevil and sort of fly by it, I can do that without feeling any kind of severe tidal forces. Because they're so large compared with my size that I'm safe to do that. If a black hole continues to eat and gets bigger and bigger and bigger, its tidal force can drop so that it no longer rips things apart. It'll still eat you, but it won't rip you apart in advance of having done so. And you know what happens? They get so big, they just eat you whole. And you don't get interesting stories about disks, about jets, about any other kind of phenomena. So we have the interesting fact that smaller mass black holes let us know of their presence because of how dangerous they are to material around them, how bloody they are to the material, what kind of violence they wreak upon material around them. Whereas giant black holes, you never even know they were there because there's some sneakier about it. Something comes by, they just gone. You're just snatched from the galaxy. The Milky Way galaxy has such a black hole. We think it's eating objects whole. We think there was a time when it might not have been eating them whole and would have made for a very interesting galactic center with high energy radiation and jets coming from it. By the way, in the early universe, back when galaxies were young, we see, looking out in space is like looking back in time, we see galaxies with active nuclei. We're, in a way, seeing the Milky Way when it was young. Counterparts to the Milky Way when they were young. When the black holes were eternally hungry. Hungry to the point where they eat themselves into invisibility. Thank you.